We are in Chapter 1, Section 1, where we discuss the background to mechanics of materials. This is the third session. In the first two sessions, we discussed action-reaction forces and plane trusses. In this session, we discuss plane frames and the method of members. Here we remind ourselves of the whole picture with respect to the first four chapters. We are now in Session 3. We look at plane frames now. Plane frames were briefly discussed at the start of this section. Plane frames are a coplanar system of pin-jointed bars. They form a rigid system. They are subjected to both axial and flexural forces. In a plane frame, members can be subjected to transverse forces in between the ends of the members. This causes bending. While trusses are solved by looking at the equilibrium of the joints, plane frames are solved by looking at the equilibrium of the members. The method of solving is therefore known as the method of members. With trusses, the forces acting are aligned with the axis of the members, while in plane frames, the forces acting are generally not aligned with the axis of the members. In trusses, we look at the external truss first. We found out the external forces and then looked at individual joints. In plane frames also, we look at the overall frame first and find out the external forces. This is done generally, but is not always the case. Then we look at the equilibrium of the members, and in this way we find the forces acting in the members and on the frame as a whole. Let's first look at the exchange of forces between the joints and the members in a plane frame. Here there's a force at pin B due to BP. Pin B reacts with an equal and opposite force. There's also a force at pin B due to ACP, and again pin B reacts with an equal and opposite force. So there are two sets of action-reaction forces at pin B. In the nomenclature used in frames, we say that dP causes an action force and ACP a reaction force. This nomenclature is different from action-reaction forces in Newtonian terms. Now let us look at the pin at C. It is subjected to a force due to ECD. Let us consider that force to be FECD. It is also subjected to a force due to ACP. Let us consider that force to be FACP. The pin C is in equilibrium, so FECD will be equal to FACP. These two forces act on the same body, which is the pin. Action-reaction forces in Newtonian terms act on different bodies. So these two forces are not action-reaction forces in Newtonian terms. These two forces are also not aligned with the axis of the members. We continue to look at the joint at C. FECD is a force due to the member on the joint. The joint will react with an equal and opposite force F dash ECT on the member ECT. This force is of more concern to us since we are looking at the equilibrium of the members rather than the joints. The pin at C will also react with the force F dash ACP acting on the bar ACB. Like these two forces acting on the pin, F dash ECB and F dash ACP has to be equal in magnitude and opposite in direction. To start with, we do not know the magnitude or the direction of F dash ECT, but we know that if F dash ACT acts in a particular direction and has a particular magnitude, then F dash ACP will act in the opposite direction and have the same magnitude. We represent F dash ECT by a horizontal and a vertical force, RCX and RCY. Then since F dash ACP is equal and opposite, the forces acting on the bar ACP will have RCY acting in the opposite direction and RCX acting in the opposite direction. Now, let us look at solving the problem at hand. To start with, we first find out the reaction forces acting on the structure. In this structure, we do not need to find out the reaction forces at A. We only need to find out the reaction force acting at B on the overall structure, which we find out to be 300 Newton. We'll consider equilibrium of ECT, ACP, and BD to find out the forces acting on the overall structure and the individual members. Now, before we look at the equilibrium of the three members, let us look at the joints C, D, and B. With the joint in C in ECD, we had earlier designated RCY to be acting upwards and RCX to be acting towards the right. As such, in ACB, RCY had to act downward and RCX had to act towards the left. In ECD, we designate RDY acting upward and RDX to act towards the right. Then in BD, RDY acts downwards and RDX acts towards the left. At P in BD, RPY is considered to act upwards and RPX is considered to act towards the right. In ACB, then RPY acts downwards and RPX acts towards the left. We now look at the equilibrium of the member ECD. Considering moment about the point P, we see that RCx into this distance plus 500 into this distance is equal to 0, from which we can get RCx. Considering moment about the point C, we see that 500 into this distance is equal to RTX into this distance, from which we'll get RTX. Looking at forces in the vertical direction, we see that RCy is equal to minus RTy. So we have found out RCx, RTX, and found the relationship between RCy and RTy. We now look at the equilibrium of the bar Bt. If we consider moment about the point P, then we have already found out RTX, and we can find out the value of RTy. So here we are given RTy, and as such also RCy. Now RTy being known, summing up forces in the vertical direction, we can find out RPy. Also summing up forces in the horizontal direction, we can find out RPx. So we have obtained RPy and RPx. Here we have the frame again. Now we earlier found the forces in ECD and PD. Here we have ACP, and we already have the forces acting at C and B. By considering horizontal forces, we can find RAX, and by considering equilibrium in the vertical direction, we can find out RAY. That means we have found out the components of the forces in all the joints A, C, B, and D. From the components, we can find out the actual reaction forces RA, RD, RC, and RP. We can also find out the directions of the forces. Tan theta is equal to RAY divided by RAX. For the reaction RA, similarly, we can find out the angle of the other three cases. So we have drawn the members and the forces acting on them. So here we see that at C, this is the force due to the pin, while at C in ACP, there's an equal and opposite force also due to the pin. The force at A acts at an angle of 19.44 degree. This is unusual for a frame, but here in BT we see that the resultant force are along the axis of the member. Here we have an example where we have a frame to which a pulley is attached and load is hung using a rope that passes through the pulley. We have a roller support here, so the reaction will be in the vertical direction. So the initial part of the problem will be looking at the forces on the frame due to the pulley. When considering the pulley, we'll look at equilibrium of different parts. So let us look at the weight first. So the weight is subjected to a gravitational force and also a force due to the rope, which keeps it in equilibrium. Now consider equilibrium of the rope. It is subjected to a force due to the weight. There is a reaction at the point where it is attached, and there's a distributed load acting due to the pulley. The distributed load can be given in terms of 2-point loads as shown here. We look at the equilibrium of the pulley. The pulley is subjected to forces due to the rope and due to the pin. The pin is attached to the pulley and the bar here. So it is subjected to forces due to the pulley and due to the bar, which keeps the pin in equilibrium. The pin reacts with equal and opposite forces on the bar. Since we'll be considering equilibrium of the members, these are the forces we are interested in. So now we have the forces acting on the members. We have three external reactions, RAX, RAY, and FP as well. By taking moments about the point B, we can find out RAY, and summing up the horizontal forces, we can find out RAX. By taking moments about the point A, we can find out FP. So these forces have been found out as given here. Here we have redrawn the whole frame again with the forces acting on it. We'll only be considering the equilibrium of the members CDE and ADP. Now let us look at the joints. The joint D is connected to both CDE and ADP. In ADP, we assign the direction of RDY as downwards and RDX towards the left. Then in CDE, RDY will act upwards and RDX towards the right. We also arbitrarily assign direction of RPY and RPX, and also RCY and RCX in ADP and CDE. Now let us look at the member ADP. Let us take moments about the point P. Then we see only RDY, and this 125 Newton causes moment about the point P, from which we can get RDY. Now let us look in the member CDE. So if we take moments about the point C, then we'll be able to find RDX. So in CDE, we know RDY and RDX, and solving forces in the vertical and the horizontal direction, we can find RCY and RCX. With RDX and RDY known, in ADP, we can look at horizontal forces to find out RPX and vertical forces to find out RPY. This gives us all the components we need at the joints. With the components known, we can find out the reactions, say at C and D as well as B. Here we have an example of an ice stone that holds an ice block which has a weight of 1000 Newton. To start with, we see that the force in Fg will be 1000 Newton and the vertical force acting at P and A will be 500 Newton each. The ice tongue is symmetrical. The horizontal distance between F and D is A, and also the horizontal distance between F and E is A. The vertical distance between E and C is small c. Also, the vertical distance between C and A or P is small d. The width of the ice block is taken as 2p. Due to the symmetrical nature of the tongue, DFE is an isosceles triangle. A perpendicular drop from F will bisect DE. Since this angle is 120 degrees, the angle made by this perpendicular with DF will be 60 degrees. Since the horizontal distance between D and F is A, using tan 60, we find the vertical distance between D and F as 0.577 A. We'll now consider the equilibrium of the members in turn, but first we'll look at joints. The joint F belongs to both FP and FE. We consider the direction of the vertical force acting at F in FT to act downwards. Then the direction of the vertical force acting at F in Fe will act upward. Similarly, the direction of the horizontal force here is towards the right, and we take the direction of the horizontal force here to act towards the left. Also consider the joint D. At D in FD, we consider RDY to act downwards, and as such, at D in DCB, we consider RDY to act upwards. Here, RDX acts towards the left, and here RDX acts towards the right. It is convenient for us to consider member DF and member FE at the same time. Let us take a moment about the point D. Then RFY into A plus RFX into 0.577A is equal to 500 into A, from which we get this equation. Now consider the joint E. Then RFY into A plus 500 into A will be equal to RFX into 0.577A, from which we get this equation. Solving these two equations simultaneously, we get RFY is equal to 0 and RFX is 866 Newton. Knowing RFX and RFY and solving forces in the horizontal and the vertical direction, we can find out RDX and RDY, and similarly REX and RUY. Here we consider the equilibrium of Remember DCP only. We do not need to find out the equilibrium of ECA due to symmetry. In DCB, we assign the direction of RCY and RCX acting at C, and also the direction of RPX acting at B. The values of AC, B, and B, which are the dimensions, are given here. Now, let us take moments about the point C in DCP. We have already found out RDY and RDX in the previous slide. So, considering moment about C, we can find out RPX. Then, solving all forces in the vertical direction, we can find out RCY, and solving all forces in the horizontal direction, we can find out RCX. This gives us all the component forces that we need to know in F, D, C, and B. From the vertical and the horizontal components, we can find out the forces in B, C, D, and E. The members D, F, F, E, and DCP are given here, and with all the forces acting on them, and we can see that the members are in equilibrium